what now? It's not working. I'm sorry. Okay, is this image, the one that's here is created by this convex lens, is it a real image or is it a virtual image? Real or virtual? Remember what describes a real or a virtual images? Yes, Adele? How much what? Well, did we have a previous chapter? We did not, right? I don't know. We might have a piece of another chapter, the one on nuclear, but I'm not sure. Probably will, because we have like a week and a half of class left, or even more, I think. Is that right? 2 weeks? So we will probably have a portion of the nuclear chapter. So if you want to go ahead and read ahead, then that's fine. Okay? Or just wait a couple of days and I'll tell you. It's a very interesting chapter, but is that the answer you wanted to hear? That's what I mean by we might have another quiz, because if we go into that chapter, then we'll have another quiz. Okay? All right. Let's see. I'll stop at 1:15. Oh, no. So remember, real images can be projected onto a screen. So, like, for example, I like to think about the projector. The projector consists of a lens. There's a lamp behind the lens, and then you have the image over here. This is a real image. So for convex lenses, real images are always opposite the object. Real images are always opposite the object. All right? So here, this is a real image. What if I have a lens that looks like this? This is my object. My image, in this case, is right here. Is that a real or virtual image? Just tell. It's a virtual image. Right, these are two different scenarios. This scenario here is like a magnifying glass. And this scenario over here is like a projector. Right, so we did this last time with the projector where you had the lens and the lamp and you make the little image. I don't think all of you could actually get the image, but a number of you saw the image of the lamp. That's like this, where you're projecting a real image onto a screen. Well, if you use a magnifying glass, you can never project the image that you have from a magnifying glass onto a screen because the magnifying glass actually produces a virtual image. Right? The magnifying glass produces a virtual image. The difference in these two is where you place the object. Let me go to the next page and I'm going to redraw these figures. So with the convex lens, I have several different scenarios. I can be outside the focal point. This is my object, and my image is over here. This is a real inverted image. It's real, and it's upside down. Over here, if my object is inside the focal point, I have a virtual upright bigger image. So in this case, this is my object. My image is going to be right here. This one is like a projector. This one is like a magnifying glass. And then finally, if I put my object at the focal point, this produces no image at all. you can draw your rays. Remember we drew some rays with convex lenses? I think we drew rays, did we not? Sorry, we're doing this in my other class too, so I'm getting, yeah, so we drew rays here. We can draw a couple different rays with convex lenses. We can draw one that's parallel to the axis and through the focal point, or we can draw one that's through the focal point and parallel to the axis. So I can do that with some of these, with the first one and the third one. If I draw a ray that's parallel to the axis, then it goes through the focal point, and then I draw a ray through the focal point, and it goes parallel to the axis. Where these two rays cross is where the image is. You should know how to draw these two simple rays for the convex lens, at least for this scenario, that you're able to draw these rays parallel to the axis through the focal point. Remember, that's how we define the focal point. Parallel rays converge there. And then the reverse of it, through the focal point, parallel to the axis. Okay? Where my two rays cross, give me my image. This is an inverted image. It's real, and it's like what you get in your eye, right? You get this type of image, which is a convex lens on your eye. It's an inverted image, and it's a real image. The magnifying glass, I'm not going to try to draw the rays for this. These are kind of complicated because you get what we call virtual rays, and you don't need to know about that. But anyway, the magnifying glass is a virtual image. It's always upright. It's always bigger. And then if I'm at the focal point, I can draw a ray. Don't worry about this. I'm not going to ask you to draw these rays, but I'll show them to you here. I can draw one through the focal point, and then there's another ray that we can draw, which is just through the center of the lens, and it goes through unrefracted. Notice that these rays are parallel. Parallel rays will never cross. So the scenario where you get here is if you have a convex lens or a magnifying glass, as you're looking at something, there will come a point when your image is just really fuzzy. That means that your object that you're looking at is actually at the focal point. Okay? Um, we have some sign conventions for these things. Well, give me just a second. Let me look at my notes. Because like I said, I do these different. Yeah, well, let's do the sign conventions. They are kind of important. So we have a couple of equations that we'll use for this. Our our lens equation, 1 over f is 1 over di plus 1 over do. And then we also have an equation for the magnification. That's negative q divided by, negative di divided by do. Remember, f is our focal length. Di is, gosh, what is di? What is di? The image distance, right? And then do is the object distance. It's the distance from the lens to either the image or the object. So as we're looking back on these previous figures, if I were to draw my object distance, it would be here. This would be do. This would be di. This would be do. This would be di because it's to my image. And then here I have do. And it turns out that di, if you try to calculate it, is equal to infinity. That means the image never exists. It's always at infinity because that's where parallel rays cross. Okay? Be able to label those on a figure if I show you an object and an image. Know what the object and the image distance are. This other thing that we have, this is the magnification. The magnification describes how the image is relative to the object. If I have a positive magnification, that means it's upright. If I have a negative magnification, that means it's an inverted image. Right? If I have a magnification that's bigger than 1, looking at the absolute value of the magnification, positive or negative, is it negative 2 or is it positive 3 or whatever, if my magnification is bigger than 1, that means the image is bigger than the object. And then if I have a magnification that's less than 1, that is the absolute value is less than 1. So anywhere between -1 and +1, right? Zero point 0.5, -0.5, 0.8, whatever. If my magnification is less than 1, then as you might expect, the image is smaller than the object. Know what the signs mean and the values of the magnification. So for example, in the test, I might give you a question that says, this lens has a magnification of -3.4. And then I would ask you to describe what is the image like. Is it upright or inverted? It would be -3.4. It would be inverted, right? And would it be bigger or smaller than the image? It would be bigger, right? So let me write that. So let's say, for example, this is my object. This is my object. If my magnification is equal to -2, my image would be twice as big and inverted. Whereas if this is my object and my magnification was equal to +1/2, my image would be upright and half the size of the object. So this is the object, this is the image, the image. Okay? The value of the magnification gives whether it's bigger or smaller. The sign of the magnification gives whether it's inverted or upright. Okay? All right. One more thing regarding sign conventions. And let's see. Yeah, when I say absolute value, I just mean strip away any negative or positive information. Okay, that's fine. Yeah, once you see it and once you sort of practice with it a little bit, I think it becomes fairly straightforward. Now this isn't quite as straightforward, but because we just sort of make it up. If di is bigger than 0, that's my image distance. If I calculate it to be bigger than 0, that means that I have a real image. If di is positive, I have a real image. If di is negative, I have a virtual image. If di is bigger than 0, I have a real image. If di is less than 0, I have a virtual image. That's just a convention, and it's the way that it works. So if I have a positive image distance, I'm dealing with a real image. So this projector, if object, lens, image, that is a positive image distance. It is a real image. If we're looking at a lens like this, if this is my object, we're going to sort of call this virtual space, and we'll call this real space. Those aren't really technical terms. It's just sort of something to help us think about the values here. In virtual space, Q, or excuse me, DI, is always negative. So I have a negative DI over here. I have a positive DI over here. Real images are on this side of the lens. If my object is over here, real images are always opposite the lens. Virtual images are always the same side as the lens. Knowing those three scenarios with the convex lens will help you with that. There is, by the way, some ray diagrams for the concave lens, but they're a little bit different, and we're not going to draw those. They're a little more complicated. Okay, let's look at what happens with the eye. So if we look at that thin lens equation, 1 over f equals 1 over di plus 1 over do. What are things here that change for the eye? Well, I know that the object distance can change, right? Because the human eye is actually pretty remarkable. We can look at things really close to us, and then we can also look at things really far away. If you're dealing with a camera, right, you have to change your lens out. You have to, well, shoot, I gotta get a new lens, and I can see, you know, that thing 50 feet away, but I can't see that thing 1,000 feet away. But with the human eye, you can see pretty well at a large range of distances. We'll also see that the human eye can see at a very large range of intensities. Have we talked about this? Okay. Like I said, we're doing this in my other class, and they sort of do different topics than y'all. But anyway, the human eye can it can see very bright things, right? Like you can go out on a bright sunny day like today and you can see things. But if I were to put you in this room and turn out all the lights and I was able to close all the windows and make no light at all, and then I was able to release just a couple of photons into the room, just a couple little pieces of light into the room, the human eye can detect that. Isn't that cool? Can you imagine? Just a little bit of light and the human eye can detect it. And we don't have detectors that can do that for sure. Or we have detectors that can detect a single photon, but you take them out on a sunny day and they're zapped because they'll just be overloaded and they'll just die, those detectors. And not only that, but you know, the human eye lasts for about 80 years or so. Typically, you know, you might have some issues, but for the most part, it lasts for many, many decades. And any instruments that we build, you know, just last a few years. So anyway, that's my rant about the eye. What is my object distance changes on the eye. Does my image distance change? Does the image distance for the eye change? Let's sketch what the eye looks like. So I have a lens. It's a convex lens. It's actually made up of a couple of different parts, and we'll get into that. And then the image is projected back here on your screen, aka the retina. I guess screen should go in quotation marks, right? Anyway, the image is projected onto the retina. So what are the things that change here? The object distance changes. Does the image distance change for the eye? No, because the shape of the eyeball doesn't change unless you have some major trauma or whatever. So di is always constant. For the human eye, the distance from here to here, di, will remain constant. So I can rewrite this equation. I can say 1 over di equals 1 over f minus 1 over do. This over here is constant. This will always remain the same. And then if I change one of these other variables, say if I change the object distance, I make it go from far away up to near to my eye, then f will have to change in order to compensate for those different object distances. So here, do, the object distance, will change because you want to look at things that are near and far. And then f, the focal length, will adjust. Who was that? All right, f will adjust to uh, give a focused image or a clear image. Okay, so if do increases, what happens to f? Let's see. If do increases, what happens to f? Does f go up or does f go down? If do increases, what happens to f? Now think about this equation here. I'm making this value go up. And so this value will have to compensate in a particular way. Now, it might be different than what we've done before, right? Because we have inverses here and not direct relationships. So if do goes up, what happens to f? What happens to the focal length of your lens? While you're doing that, I have an eye in my office. I'm going to grab it. So grandfather's eye. He's a very large man. Okay, so what will happen here? All right, I'm going to stop at 130. Okay, so it looks like we're sort of split. Most of you thought that it will go up. So if DO goes up, what happens to this term? I have this 1 over DO. If DO increases, this whole term does what? Does it go up or down? It goes down, right? So like if I have a half and a third, which one's smaller? The third is smaller. Because if I have a big number in the denominator, that means that term is going to go down. So if DO increases here, that means this term goes down. So I need to think about my focal length. I want that term to compensate to go up. So if I have 1 over f, because I know this difference has to remain constant, I want this whole term to go up. So what am I going to have to do to f in order to make that go up? Does it go up or down? Right, so in order to make that value go up, I have to make f go down. Okay? Think about this in the eye. Well, I'll sort of sketch it here in just a second, but it does help to think about this in terms of the equation mathematically. So here, my focal length will actually go down. So B is the right answer. Let's think about the eye. So I have the eye here. I have this convex lens. The focal length, remember, we'll see that the focal length of the eye is adjustable. Let's say that I have something that is really, really far away. Let's say that DO actually is equal to infinity. When the light rays reach the eye, how are they going to be traveling? If I have something, if I'm looking at something really, really far away, how are they going to be traveling when they reach the eye? Rhymes with, I don't know what it rhymes with actually, huh? They're going to be parallel to one another. Okay? Yeah. Okay, so when light rays are, when an object is really, really far away, like the sun, when the light rays reach us, they're going to be parallel. So I can imagine light rays coming from this thing, and they're going to travel like this, parallel to one another, if something's really far away. And then they're going to focus at what point? Light rays that are parallel focus at the what? They do focus at the retina, right? My image has to be formed at the retina, but further, they're going to cross at the focal point. So when I'm looking at something far away, my focal point is at the retina. Let's put that in words. When the object is far away, the focal point is at the retina. When the object is far away, the focal point is at the retina. Hey, have y'all ever taken a magnifying glass and taken it outside and tried to set fire to things with the sun's rays? Have you ever done that? Like an ant or something, or maybe not a living creature, but you know, like a leaf or something, or a piece of paper. It was an ant. Okay, good. Yeah, my son, he had a little magnifying glass, and we were out with it one day, and we were setting fire to things, paper and leaves and all sorts of things out in the yard. And I thought, gosh, I wonder how hot it would be. Did I tell you all this? I wonder how hot it would be. Like, how hot is that little point of light? And so just for a second, I just sort of slid my hand into where that light was. And let me tell you, it's very, very hot. Okay, that's one of the reasons you should not look at the sun, because when you look at the sun, it focuses all of the light's rays onto your retina, and it can just take a small amount of time to burn the back of your eyeball, like those ants that you killed when you were, they bite you. Okay, so it's okay then. All right. So when the object is far away, the focal point is at the retina. When the object is nearby, this is where knowing how to draw those rays will help you sort of think about this. If I have an object that's nearby, like this, my rays are going to go a little bit differently. Here, my focal point is actually going to move in, and then I can draw my rays parallel to the axis, through the focal point, through the focal point, parallel to the axis. So here, I get an image that is, gosh, is it real or virtual? It's a real image. Remember, real space, or excuse me, virtual space over here, real images are formed over here. In the eye, you always have a real image. If your eye formed a virtual image, which it can form a virtual image, but you can never see it because it doesn't project onto the retina, right? In fact, actually, uh, if your eye did form a virtual image, that image would be right here, right, really close. It would be like your magnifying glass, that scenario that we drew earlier. So here, if I'm looking at something up close, the focal point moves in. So when the object is closer, the focal point gets smaller. So physically what's happening here is, in this case up top, I begin, I'm going to exaggerate this a little bit. I'm going to draw over and exaggerate it. In this case up here, I begin with a lens that's really slender. And then down here, I have a lens that's really wide in the middle because my focal point is actually getting smaller when I come here. And a lens with a smaller focal point is wider in the middle, as opposed to up here, where my focal point is longer, so the lens is slender in the middle. Think about those circles that come out. These have a longer focal point than these do. Let me pass around this eye. This comes apart, and you can feel free to take it apart. We'll get into the different parts of the eye, and you'll probably studied it in anatomy. But right now, we're just concerned with the lens. This is, gosh, what is this called? This is the cornea, right? That's outside of your eye, and that does most of the refracting of the light. Most of the bending of the light occurs with this. Because the light is moving from air to this material, which has an index of about, I don't know, 1.3, 1.4 or so. And so that bends most of the light. Most of the bending occurs there. But then inside your eye, oh, there we go. Inside the eye, does this come apart? It doesn't. You have another lens right here, right? And this also adjusts. There are little muscles attached to it that cause it to squeeze down or pull out. This is the lens. It also refracts the light less so, but this is actually what changes when you change your focal length of your lens. So those muscles will push down on it and make the focal length what, bigger or smaller? If they push down on it, it's smaller, right? They make it wider in the middle by squeezing it down, and that gives us a smaller focal length. Or they stretch it out, and that gives us a longer focal length when we want to look at the sun or whatever. Okay? But not directly at the sun. That's very bad. So y'all can pass this around, and feel free to take it apart. Look at the different parts. You will have, as you had on the quiz today, you had identification on that quiz, and you'll have that on the test coming up in a couple weeks or so. Okay? All right. I think that we will stop that there. Well, we have to do something else. We have to do evaluations today. 20, come on. 20 minutes, it should be plenty of time. You should get out a little early. But I want to tell you a little bit about them. I know that you hear this, and you should have been doing evaluations in your other classes. Am I right about that? Yeah, so you have two parts to this. You'll need a pencil, Bria. All right, I have one up here. Does anybody else need a pencil? Anybody need a pencil? I'll pass that back to Bria. All right, look, guys, you have two parts. You have this part, which is just open comments. The open comments are you just criticisms or things that you like about. Yeah, hold on just a second. So about the comments here, they take these and they seal them up in an envelope and they send them straight back to me. It won't affect you, but it will impact students that come into the class next year. So anything that you like or that you'd like to change about the course, please record that here. And I really appreciate any critical things because that's useful for me. I usually go through these and try to look for 2 or 3 things to change for next semester. So if you like something needs to be changed, this is the place to write it, okay? And then we also have this. You'll need to put in the CCN number, which I'll write on the board. That's going to be your SIR report number. I'll write that number on the board. That's where I never actually filled this out. Yeah, and answer the questions and bubble it in with a pencil. Do I need a pencil? Yeah, I'll get you one in just a sec. Okay? This goes through all the various administrations, and I look at the numbers, and it's useful in its own way, but please take your time on both. Okay, I also need somebody to take these to the dean's office, the dean, College of Arts and Sciences. He's right over here. Who's willing to do that? Just pack up everything in an envelope and take it to the dean's office. Okay, Bria, thank you. Listen, there's a big envelope up here, Bria, and you can stay right there, but just put everything in the envelope when everybody's done, and then take it over to the dean's office. You know where that is? College of Arts and Sciences? Just go in this door, take a right, and it's right there in the corner of the building, close to the street. All right. Actually, here, we pass those out. We pass these out, Morgan. 151. So I'm going to have to be here for another minute. I'm not really supposed to be in here because